Ismael Morales, who's going to talk about towards the profinite rigidity of surface.
Thank you. It's an honor to be in this conference, so I would like to first thank the organizers for the opportunity to speak here. The motivating question is the following. First say that this is joint work with Dave team. Is this size okay? Because I would probably write it smaller.
And make it bigger.
Oh, okay. Right. The question is related to Remeslenikov conjecture, which was stated in previous talks, also during this workshop. So this is basically asking, are surface groups profinitely rigid? Okay, so this was, I think, first time I saw this in this famous survey of Alan Reed. Probably first articulated there and put it in comparison with the question of whether free groups are profinitely rigid. There are similar difficulties that appear when studying these groups. Somehow this representation theory machinery also breaks down for these groups because there are many ways to see them as lattices, arithmetic lattices in PSL2R. In various ways they are close to free groups. And I will first like to state a fantastic theorem of Wilton from, I think it was published 21, which is a result which is about the relative profinite rigidity of surface groups. So if you take a limit group, and you know that the profinite completion is the same as that of a surface group. I didn't say it, but for the rest of the talk, a surface group is just going to be pi1 of a closed surface. I'm not including free groups as surface groups. Okay, so Wilton proved this for free groups, and the same proof actually gave him this corollary that this mysterious limit group L has to be isomorphic to a surface. Okay. So the way he proved this is by showing that basically such an L has to be one-ended. I will explain this why this is the case. This is important in our argument as well. Such an L will be one-ended, and limit group. Wilton proved that one-ended limit groups contain surface groups. You can see them in the profinite completion, and this surface has to be very big in L. In fact, have to be finite index, and from there, it's not difficult to see that L will have to be a surface group. And once we know that L is a surface group, because surface groups are distinguished between each other by the profinite completion, then we know that we have this isomorphism. Okay. So, okay, one theorem I want to talk about today. This is with Aikin. It's about relative profinite rigidity as well of surface groups in dimension 2. This is let G, so we have the usual assumptions, be a finitely generated residually finite. We're going to suppose that G has cohomological dimension 2 and vanish in second order Betti number. And then the theorem says that in this setting we can recognize surface groups by the profinite completion. Okay. And then one corollary of this is that if G is a finitely generated residually finite one-related group. So this is to give one example of a class of groups where we didn't know rigidity of surfaces before this statement. And this will maybe explain why these hypotheses, which might seem a bit artificial, they show up in different situations. So we'll give two corollaries to this. It applies to one-related groups. And you can also prove the same conclusion for limit groups. And this uses, so using the work of Sela and also Karlampovich, Myasnikov, this hierarchical description of limit groups. You can also get as a corollary. This is not a corollary of this theorem, it's a corollary of a statement that I'm not going to mention, but it's a corollary of the proof. That limit groups, so surface groups are recognized among limit groups by only looking at finite solvable quotients. So we don't need all the finite quotients in principle. So I will write this as, so this is going to be the pro-solvable completion. I won't talk about this during the talks. I will just say. This means that these two guys have the same finite solvable quotients. Okay, so they will have to be isomorphic. And I think the surface subgroup approach of Wilton doesn't give you this conclusion in principle, as far as I know.
What did you say about the work of Sela?
Yes, so for this to be a corollary of our theorem, I need to show that limit groups have this vanishing. So we need much less, but I don't know how far it is. Yeah, we need this condition for limit groups. We need this. And there are higher dimensional limit groups, but okay, first you have to show that L doesn't contain Z square. Once you know L doesn't contain Z square, you're hyperbolic and you are two-dimensional. Okay, so you land in this theorem.
In the one-related corollary, how do you rule out one related with torsion which wouldn't have CDs too?
So this, I mean, any group with the profinite completion of a surface group has to be torsion-free. So you know that you are in the torsion-free case. You take a one-related group, might have torsion, but because G embeds here, it is torsion-free. So you are in that case. You are not in the torsion case. So, okay, as I said, surface groups are distinguished between each other. So all we have to prove to get this conclusion is that G is a surface group as well. How do we access this? How do we prove that something is a surface group? We use Poincare duality. Okay, so we're going to use this theorem that two-dimensional Poincare duality groups are classified. The work from Ekman, Linnell, Mueller. I'm going to put Bowditch as well because we use a mod P version of this. If a group G is Poincare duality, dimension 2 over Fp, then G is a virtual surface group. So if you are also torsion-free, you will be a surface group on the nose. All right. And in order to verify this, it amounts to check. So how to prove? Let's say we take one related group. How to prove that it's a surface group? We prove its Poincare duality. This amounts to check two cohomology groups. I'm going to use the definition of Poincare duality that I think Farrell started using. So we have to check that this cohomology group vanishes and that this second cohomology group with coefficients in the group algebra is a trivial G-moment. Well, this is a Savilian group. Okay, you would have. It doesn't really matter. It might be non-orientable, but you can always pass to finite index subgroups. So you're going to prove that this guy is a trivial G-module and it's just a one-dimensional over. Let me start with the first group, and this is related to Andrei's talk yesterday. So from yesterday's talk of Andrei, we know that this cohomology group encodes the derivations of G that land in the group algebra. So if we get a non-trivial element in this cohomology group, we get a non-trivial derivation, and this gives us free splitting. Okay. So if non-zero, we get a free splitting. Because recall that G is torsion free. We get this assumption from free splitting. But this is not the case, and I want to briefly explain why we know already for granted that G is freely decomposable. And this is one of the main differences when it comes to study profinite rigidity of free or surface groups. We don't know if there's a one-ended group with the profinite completion of a free group, but we know that any group with the profinite completion of a surface has to be one-ended. That at least the number of ends, in this case, we can detect. Okay, so the proof is very simple. Suppose not. Suppose that G is the free product of two non-trivial groups. Then we see the same free splitting in the profinite completion. And now there's an old argument of Serre, or something that he proposed as an exercise. That if you take an infinite index subgroup in a PD2 group, this is going to be free. So the P cohomological dimension of both factors decreases. So this is like the Pro-P version of this theorem of Farrell, that infinite index subgroups in Poincare duality groups have a strictly smaller cohomological dimension. And from this, now you can prove that the P cohomological dimension of the completion is also at most 1, and this is a contradiction. Okay. Okay, so this proof is the vanishing of this group. Okay, now I'm going to talk about the second one. So the second one is the complicated one. But before that, I need to introduce what is cohomological goodness. Maybe already.
Excuse me?
Yes.
One question. So there's two hypotheses in your theorem. To what extent are these known to be or not to be profinitely varied?
Okay, I was going to talk about something related at the end. Is the second known? I think Bolger. The second is not a profinitely variant. Okay. So I think the second and all the higher eligibility numbers are known not to be profinite invariants. I
Even
think
with good finiteness properties.
Yes.
well, if you are FP3, okay. If you have look approximation, you can. No, you need goodness also. No, in general, they're not. Okay, you can add some artificial.
Okay.
But if you are good and FP3, then you get this.
And for the cohomological dimension?
And yeah, the cohomological dimension, this is very difficult to obtain.
Okay.
Very complicated. Yeah. So you would expect, okay, if I get a three-dimensional group, it is even farther from a surface group, so it should be easier to prove that completion cannot be this, but we don't know how to do that. Yeah, controlling the cohomological dimension is very difficult. And in fact, this Remeslenikov conjecture is telling you that having dimension 1 is a profinite invariant. So, cohomological goodness. We say that a group G is P good at a prime P if the restriction map in homology from the profinite completion to the group itself is an isomorphism for all finite modules so M is P torsion in this setting, and for all integers I. This is the definition. Usually we get a restriction map. We don't know if this map in general is surjective, but we always know that this map is injective, and this will be useful for us. Let me recall. There's a correspondence between the lattice of open subgroups of this guy and the lattice of finite index subgroups of G. So if I write finite index subgroups of G by taking the closure inside G hat, we get the set of open subgroups. Okay, and using this correspondence, you can simplify this definition. I'm going to restate it as follows. You are going to look at similar maps, but now all the modules are going to be triggered. Okay, so now this is. Now for every finite index subgroup, you have to check that these are isomorphisms. And yeah, so in our setting, we're in dimension 2. So we only have to care about the case I equals 2. Since we're in cohomological dimension 2, and for I, these maps are always isomorphisms. I mean, these are just the P abilinizations, which you can detect by finite quotients. You put these two things together, and you only need to study the second cohomology groups. Okay, but also, and this is a very nice fact, that in general this map, so these restriction maps, this is one, second, these restriction maps are always injective. So we only need to prove that they have the same FP dimension. you have an injection between vector spaces of the same dimension, that would be an isomorphism. So somehow the functoriality properties of this map are already here and here. We just take the injectivity, and now we don't understand the map. Now we are only looking at, sorry. This is usual cohomology U is an abstract group. Okay. So now we only have to look at these guys. 1 plus 2 imply we need to show that this second cohomology group for every finite index subgroup is 3. This is all we know, all we need. Right here. Is there any question about this? Maybe So we know the left-hand side because we know the profinite completion. This is maybe I should make a remark. So U hat is the so U hat is an open subgroup of this profinite completion, right? So we know that this is also a profinite completion of a surface, okay, some finite cover of the original surface. So we know the left-hand side always by assumption. We only need to prove the right-hand side has the same dimension. This is what I meant, and this is why I'm assuming orientable. We can just assume that the surface was orientable in the first place. So there's, by the way, in the case I equals 2, there's a very nice proof of Gareth Wilkes in his thesis of this injectivity using central extensions. It's a very short, I won't explain it now, but it's very instructive, at least this in degree 2. Okay, so how to prove this? How to prove this claim? Let us focus. So G is P cohomologically good. G is P good. This is our claim. And first I'm going to prove it for one related groups. G, well, we know G is torsion free, so G is type F. Lyndon proved that in this case the presentation complex with just one cell is aspherical, so we know that G is of type F. And this will be useful for later, because this implies that the Euler characteristic of G is the same as the L2 Euler characteristic. This is the usual. This is the Euler characteristic. This is the alternating sum of Betti numbers. Okay, and here I'm looking at mod P Betti numbers. And the right-hand side is the alternating sum of the L2 Betti numbers. And in general, there's no way to compare the two Euler characteristics, but if you are, if you have a free resolution, then you can do it. And this will be a problem in the general case, because in the general case we don't have a free resolution. So maybe I should, okay. I think I should make one comment first. At some point, I have to say what is this division ring. So it follows from theorem of Andrei Chaikin as well that G is residually P. A group with a profinite completion of a surface group, just knowing that you're residually finite improves that you're also residually P. And once you know this, it's not hard to prove that you are reefers. You can prove that G is inside its pro-P completion, and these pro-P completions are reefers. There's no homological torsion, so it's basically like being residually solvable. And once you know that you are reefers, I will give a description of the division rings that we need to approach the right-hand side. So we approach L2 homology via these linear division rings. I will use the old definition of this division ring at Mat 7 Neumann. It's an embedding discovered independently, I think for something in the 40s, right? Given a biorderable group, okay, so this just means that I have an order in my group such that it's respected by left and right multiplication. Maybe just say that. Biorderability means exactly this. You have an order in your group, and bi order means that right and left multiplications of elements respect this order. So given a biorderable group, you have a construction of power series. You can look at this huge combination of elements G with coefficients in the ground field, such that the support is well ordered. So every subset of the support has a minimum element. Okay, so you don't allow any kind of support, you don't allow any crazy combination. You take into account the biorder in this case. And okay, so you can prove that the group algebra embeds in this object, but there is some work in showing that this is actually a ring. You can think of how to multiply things here. You can multiply elements of G. By additivity, you can extend this multiplication, but it's not clear that it's well defined, okay, as a ring. But once you have that this is a ring, and this is what they prove, this is a ring, it's not difficult to prove that it's in fact a division ring. And the linear division ring that I'm going to talk about is going to be the division closure of the algebra, the group algebra, in this big environment. So this is much smaller. This is an uncountable division ring. You make it big enough so you are giving yourself all the inverses, and then you have a space to embed the group algebra and define this object. Okay. Okay. So the Betti numbers, the mod P Betti numbers, in this sense, are going to be the dimensions over this division ring. Okay. And you can define the L2 Euler characteristic in the same way. You have usual Betti numbers, you have L2 Betti numbers, it's the same alternating sum. And for one-related groups, because they are free resolutions, they are the same. But I will later explain why, in the general case, you can still get that equality. Okay, but for the moment, we are assuming that G is a one-related group. So what is this? quantity is 1 minus the first Betti number plus the second Betti number. What is the L2 Euler characteristic? Is the 0th L2 Betti number minus the first L2 Betti number plus the second. Okay. Now, the 0th and the second vanish in a one-related group. Several ways to prove this. Once we know that this refers, and to assume this for the moment. And the nice thing about knowing that, the nice thing about this equality is that the right-hand side, so the L2 Euler characteristic, this can be computed by Luke approximation.
Is this mod P, or is this all over mod P, these numbers?
Yeah, this is why I'm regretting to choose mod P now. Thank you for the note. I will say something. Okay, so the usual Luke approximation tells you how to compute the usual L2 Betti numbers. Yeah, so you would build this ring with coefficients in Q, characteristics here. And here you also have Luke approximation, but that's a different story. I will say a few words later on. But you can still write this as a limit, the usual limit of usual Betti numbers, normalized usual Betti numbers. So this is detected from G hat in any case. But yeah, it's a mod P Luke approximation. You're right. Okay, so we're almost done because, because 2 of G, the second Betti number can be expressed in terms of first Betti number minus 1 minus this Euler characteristic, which is just this. Okay, so we have expressed the second Betti number in terms of things that we can read of G hat. Okay, and you can check now. This is you can check. This is 1. I mean, this, sorry. Here's some sign and plus minus. Plus. No, it's not okay. Yeah. Yeah, thank you. Yeah. So if G is, for instance, if G hat is the profinite completion of an orientable surface of genus G, this quantity is going to be 2G minus 1 minus 2G minus 2. It's 2G minus 2, I think that's right. Okay. And so this proves that G is cohomologically good for a one-related group. But again, I was using these two quantities are the same. I want to give one tool for how, in general, these two quantities are equal, even in the absence of Fourier solutions. I will pause for questions. So is the argument clear for one-related groups? This is goodness of one-related groups under this assumption that completion is a surface. I'm not sure about the bounce like solitaire groups, I guess. I don't know if all of them are good.
A lot of them are.
The question whether there are non-good residually finite unrelated groups is an open question that was asked.
There are non-good ones, yeah.
If you drop the residual finiteness assumption, it comes to work with the question of goodness, then there are topics of assumptions. Yes.
there are non-good examples, but usually finite is always the case, but we don't know how to prove that. So we go around that question. So now I'm going to talk about the proof of goodness in general. So in general means that you are going to use the homological dimensions 2 and the second alternating number vanishes. Okay, so we're going to, so G is finitely generative. We are going to take a partial resolution. So if it has D generators, we can write a partial resolution that looks like this. We want to complete it. We just take the kernel, this map. And because of homological dimension equal to 2, we know that P2 is projective. But we also know by the argument of Hyken-Linton that P2 is in fact finitely generated. Okay? So it's a finitely generated projective, but we don't know if P2 is free. If P2 was free, the same argument would work as here. So how do we compare, so to prove quality of Euler characteristics, we need to compare two-dimension functions for P. So we can twist P by the division ring. Or we can twist P by FP. And so the question is if these two numbers, these two positive, non-negative numbers are the same. If we know this, then we are done by the additivity of the Euler characteristic. Okay, that's what we need to show. And here we're going to use the work of Kohn. So, okay, there are several ways in which you can express the uniqueness of this object. There's this property of Hughes that describes these division rings in a unique way. It's a Hughes-free property. But also Kohn gives you a method to compare different division rings, even if they don't have this property. Okay, so Kohn allows you to sort of interpolate between different embeddings in the following sense. So this is this idea of specialization. So we'll just give one example. For instance, you can map set to FP. Okay, this is one map from a ring to a field. And you can also map set to Q. Right? But how do you compare Q and FP? This is somehow what we are doing. We're thinking of Q as the big division ring where we live, and we're thinking of FP as a sort of degenerate quotient of the group algebra. So the way you compare them, you can put something here in the middle. You can localize set in the complement of this maximal ideal. Okay, you localize the complement of the maximal ideal, and now you have this common map. Now this is a local ring. We construct a local ring from which we see Q and we see FP as well. Okay, so he actually proves the same in general. So there's going to be a local ring inside this division ring which surjects onto FP. And why is this local ring better than the group algebra? Because it's local, and we know that there's no Whitehead torsion at the end of these resolutions. I mean, when we do the cohomology over local rings, we have this old theorem of Kaplansky that finitely generated projective modules over a local ring are free. So we tensor the projective by R. Now this is a free module. So we get rid of now free projectives, which was also an issue in last talk, Julian as well. So here we can do it like this, and okay, once you have this isomorphism and once you have this diagram, you can check that. You can check this and prove these isomorphisms. Okay. So from R we can see in a satisfactory way both this huge division ring and FP. This hopefully explains part of the proof of goodness in this setting. So recall that the way you usually prove cohomological goodness is you make use of a hierarchy. Once you have a hierarchy, there are natural topological conditions you can impose on the hierarchy, like call this being efficient and so on. And you can prove inductively on the hierarchy that a group is cohomologically good by these Meyer-Vietoris arguments. But there aren't really many methods to prove that something is cohomologically good. And here, we don't have any hierarchy for G. G is just a two-dimensional group, okay, which happens to have this vanishing. So I don't have a lot of time. But, okay. I'm going to take the opportunity to ask some general questions because I think there's no official question session. So we'll change slightly topic, and I will pose some questions on the power of some homological invariance. But before that, I will pose for questions if there's any. Given the role played in proof of goodness, given the role played by the Euler characteristic, I want to ask this in general. So given a group of type F, P, over your favorite ring. Given a group of type FP, well, maybe to define, okay, for everything to be well defined, is the usual Euler characteristic the same as the L2 Euler characteristic? Okay, so this is one question I want to ask. There's something called Bass conjecture that was solved for two-dimensional groups and some more groups, but not many, that concerns the problem of looking at projective modules and twisting not by this local ring. You would twist by the Ruppel-Neumann algebra of QG. You twist by the Ruppel-Neumann algebra, and you ask if this is now a free module. Okay, so with a sort of similar argument in exclusive, like characteristic 0 setting, you can get some qualities like this as well. But we don't know many groups which satisfy these Bass conjectures and so on. But I will refer to Ekman, the work of Ekman. Ekman's work on pass conjecture. And now I also want to ask so here we also exploited the invariance of the first Algebraic number. I also want to ask it once again. I think it's still very annoying that we don't find counterexamples, and we suspect might actually be true. So if you take two residually finitely generated groups with the same profinite completion, do they have the same algebraic number? So this is more in the line of Holger's talk. So this is a multiplicative invariant that also sometimes gives you information to distinguish groups, also in geometric settings. But we don't know this in general. If the groups are finally presented, you have Luke's approximation. But but in general, we don't know. Okay. I actually want to ask. Okay, I want to ask a more specific question than this, which is going to be about the vanishing of the first algebraic number, and I'm going to relate it to detection of direct products. So this is. Well, maybe I should say also that this holds as well if your groups are residually, if they are reefers, for instance. If they are locally indicable and amenable. You can prove this using universality of these division rings, work of Hykin, and you can also use this old inequality of Kasdan. So Kasdan inequality gives you one side, and the universality, so similar arguments as we did here, gives you the other side of the inequality. You recover Luke approximation this way as well. For finitely generated, you don't need finite presentability. And I want to ask something more specific. This is question 1, question 2, going to be question 3. If, again, gamma finitely generated, principally finite, if this splits as the product of two infinite groups, the profinite completion splits as the product of two infinite groups, does it imply the vanishing of the first algebraic number of gamma? And this should be put in comparison with this theorem of Gaboriau that in the discrete setting, okay, in the discrete setting, he proved that if you have a big, finitely generated normal subgroup, which is not finite and not cofinite, then you have this vanishing. So in particular, if you split like this, if gamma splits like this, you get vanishing. But I'm not asking about gamma. I'm asking about the profinite completion of gamma. Okay. So this is it's kind of a particular instance of this question, but I would like to know if this particular instance is where it is true or if it's true at all. And maybe I will give one motivating reason why I got to this question.
Thierry, Do you know examples of groups whose profinite completion is a direct product but the group is not?
I think there are examples in like the solvable world. I think Nikolai gave me examples of
growth and pairs.
of growth and dispersion,
So
of course.
it's a product
Yeah.
Yes.
Yes.
Generally,
But,
arithmetic.
Yeah. So there are, in fact, the remark I was going to make is going in those lines towards detection of direct products. And I have several examples, but I will just give one and see, because I think we're running out of time. But at least one of the main motivation is this conjecture in this recent survey of Martin Brightson, whether so it's about profinite rigidity of the product of two free groups. So you take a finally presented, precisely finite gamma, whose completion splits as the direct product of two free groups. Does it imply that gamma is isomorphic to its products? There are examples of Tavgen, Platonov, that show that finite presentability is necessary. Okay, there are these growth-ending pairs. There's infinitely many inside Fn cross Fn. But with finite presentability, now this is maybe a more sensible question, or something we can expect to be true. And so basically the way I got to this question is just asking something very simple. So how far is the rigidity of a group from the rigidity of the products of this group? So if we knew, for instance, that free group is profinite rigid, or say your favorite Fuchsian profinitely rigid group. I mean, we already have examples of Fuchsian profinitely rigid groups. Now you take the direct product. Is it rigid among finally presented groups? So I was asking myself this question. And so one motivating observation. I'm not going to call this a theorem or something. So Remeslenikov conjecture. You want to say that Remeslenikov conjecture implies this conjecture of Martin. And one of my motivations of this question is that if you answer question 3 when one of the factors is free profinite, then you get rigidity of direct products. And what happens really is that, so Francesco was asking if your profinite completion splits as a direct product, are you a direct product? So we know this is not the case, but I think the sensible thing to expect is that if you split as a direct product, your profinite completion, then your group might not be a direct product, but you can find your group inside such a direct product. So in fact, what you show here is that such a mysterious gamma, using the vanishing of this Tourette number, such a mysterious gamma would have to be in Fn cross Fn. And here we know everything. Here we know that for these finally presented groups, this question is true. Okay. So it allows you to, so basically this vanishing of first Tourette number allows you to produce growth-ending pairs, given these factors. And in fact, maybe I will finish mentioning that this was something that Jonathan and I proved, and Fruxte and I proved, 23. We proved this profinite rigidity of direct products for finitely, sorry, when gamma is residually free. Okay, so a residually free, finally presented group with this completion has to be Fn cross Fn. Okay, and there we use some rank gradients, some machinery for propy groups that sort of avoids the absence of look approximation and so on, and it sort of dodges this question, but I think that having a positive answer or more positive answers to this kind of question would give you more results in this sense. So yeah, I think I'll stop there. Thank you.
Do we have any questions?
Am I correct that to prove in Brightson conjecture, in question 3, then you require you can assume that gamma is also finally presented. So because in Brightson conjecture, gamma is finally presented.
Yes, but I don't apply the question to gamma. I apply it to some quotients of gamma.
Ah, okay.
Yeah, I need to apply this many times somehow to produce this. Yeah, I basically have to prove that gamma has a big intersection with the two factors, and for that I argue by contradiction. There will be some non-vanishing of algebraic numbers and so on. Yeah, so it's not clear what is the finally generated group. I mean, it's definitely not finally presented or not for free. Yeah.
Any more questions?
How much of this is easier and maybe generalizable if you assume from the start that everything is type F?
If everything is type F, so in dimension 2, so in dimension 3, we don't know how to prove that to have a group of type F. So for instance, type F, UG is type F, and cohomological dimension 3, and profinite completion is a surface. Is G good? This answers your question. So this is, we don't know. Yeah. So we prove goodness because we have to deal with one, the last homology. You know, very open.
In view of your corollary, does being a one-relator group have a chance of being a profinite property?
Sure, I'm a happy man. I mean, I can believe that, yeah, but I don't have a reason. Yeah, I know.
More questions? Not. Let's thank Ismael again.
Thank you.